Hello everyone, this is Jeff from the Ozark Mountains in Missouri, USA. Today, we're going to take a look at how to test some RCA 1802 microprocessors with this, an Arduino Mega 2560. This is a bit of a follow-up on my last video where I used this very same Arduino to test some Texas Instruments TIL 311 hexadecimal LED displays. You might be asking yourself, hey Bert, what the heck is an RCA 1802 microprocessor? Well, that's a darn good question. I'm glad you asked. Let's jump over to the computer and have a look. Oh wait, before we go, take a look down below for that rectangular subscribe button. Click on that guy and you'll be subscribed. I sure would appreciate it. Once you're subscribed, you're going to see a bell-shaped icon, and if you click on that guy, you'll be notified just as soon as I post a new video. Thanks. Okay, this time for real. Let's go over to the computer. The CDP 1802 was introduced by RCA in 1976 and was its first single-chip 8-bit microprocessor. It's a 40-pin DIP microprocessor made with COSMAC, that is, Complementary Symmetry Monolithic Array Computer Architecture. It's still currently being manufactured by Interstill Corporation as a high-reliability microprocessor. The 1802 has an architecture different from most other 8-bit microprocessors. It was the world's first CMOS microprocessor, and its clock speed can go all the way down to 0. It also uses a set of 16 16-bit general-purpose registers, which can be configured to be program counters, stack pointers, DMA pointers, etc. It was used in some early lean-burn electronic engine controls by Chrysler. RCA also developed a radiation-hardened version made with silicon-on-sapphire technology, which is used in satellites and space probes such as the Hubble telescope and the Galileo spacecraft. What made me curious about it was how different it was from its contemporaries, and I wanted to learn some more. I found some 1802 ACEs for sale on eBay, from China of course, and I bought a lot of 10. They arrived fairly quickly, and when the package was opened, it was obvious they had been sanded down and relabeled. Someone on the 1802 list used the term blacktopping to describe the process, and I think that's a pretty good description. I needed a quick way to test these chips to see if they were even 1802s or if they were something else just relabeled as such. And as luck would have it, I had the Arduino Mega 2560 sitting on the bench from testing the TIL 311 shown in my last video. Since the 1802 can run down to a clock speed of 0, it seemed like I could use the Arduino to provide the clock and other inputs while monitoring all the outputs. A simple no-op program could be used for a quick test. This program wouldn't do anything, but the program counter would increase. And we could monitor the address bus to make sure that was happening. This seemed like it could be a plan. After getting the simple test rig going on a Saturday afternoon, I bragged about it on the 1802 mailing list, and I found out that other people had already had similar ideas. A fellow named Mike from the list showed off his Pocket 1802 where he used a 40-pin PIC microcontroller to do the same job. Another list member showed off his Arduino Mega based project, which is the Retro Shield. The Retro Shield not only works with the 1802, but there's also attachments to use 6502s and other microprocessors. It then occurred to me that a month or so ago, Ben Eater had used an Arduino Mega as a test rig for his 6502 based computer. And after some more research, I found an FPGA based board for testing vintage microprocessors as well. Here are the links, and they're also in the description down below. So I didn't have a new idea. This is just my variation on the same theme. Let's have a look. Using the initial test rig shown here, which had a hardwired no-op command, I was able to test the 10 microprocessors and find out that 2 of them were indeed bad. The 2 bad chips behaved like 1802s, but the address lines didn't respond properly, so there was definitely something wrong. I had some fun figuring out how to do this, and not knowing when to leave well enough alone, I decided to see what else could be done. I wound up wiring almost all of the I/O signals from the 1802 to the Arduino, with the exception of these 6 lines. EF1 through EF4 are inputs, and the DMA and interrupts I thought best to leave to a later day when I understood programming the microprocessor a bit better. This is an overview of how the software on the Arduino is laid out. First, we configure a default state for the I/O pins of the Arduino. Then in the main loop, we check to see if any serial commands have been entered, and we decode those if they have been. If we're in run mode, we'll read the state of the address bus and the status outputs, and then we'll decode and act on that state, for instance, if there's a rising or falling edge on certain signals, etc. And then we'll save the current states to use for the next loop for determining rising and falling edges. If we're in the system initialization mode, we'll run the clock for 64 cycles and then put the processor in a pause mode. I was just doing this to simulate a soft power on reset feature that a real system might have. Alright, enough slides. Let's go to the bench and look in the description down below for links to some of the things that I've mentioned here. I've increased the font size here, so hopefully it'll be a little more legible on the video. You might see some squiggles right here from IntelliSense. Ignore that. Sometimes it has a problem with the Arduino stuff. I'm using the free version of Visual Studio 2019 here with a add-on called Visual Micro. You can open and work with this same project using the regular Arduino IDE as well. I just find Visual Micro a little easier to use. So the project only has 2 files. There's a header file, which just has some defines in it for what pins we're using on which ports and what they do. So we can tell here that the EF1 signal from the microprocessor is wired to pin 1 of port K. Here's the main part of the program. I always try to leave some notes for myself, things I'm thinking and things I want to work on later. I'll leave that at the top of the program. Some enums just to define states of various signals and whatnot. And here I have a bunch of test programs. Then I just comment out the ones I do not want to use right now. I have a test program that reads the states of these EF inputs right here, so I can ground the input to test it. And some globals. And I like leaving myself a lot of comments or other people. It sure beats not leaving any comments in your code and a few weeks or a few months later you're trying to figure out what the heck you were thinking about. Then we do the setup where we're just configuring all of the ports though we need them, and we start our serial connection. Then we get down into the main loop. So we check to see if we've entered any serial commands, and then we check for the run state first, and we do things in this order because if there's a serial command we want to act on it first. Then if we're in the run state we want to process all of these things like looking for the rising or falling edge of signals, reading the current state of the inputs, acting on those things for reading or writing to memory. I've labeled each one with a letter to designate that it's something different. Reading the state of the N0 through N2 outputs, and looking for the Q port rising or falling edge. The delay sets a loop delay so we can slow down the program execution. We increase the clock, and these are 1/2 ticks, not full ticks of the clock. And then we save our current state for the next time so we can detect rising and falling edges. And I've made myself another note here that I don't think we actually need to save the address bus state. And finally, at the bottom we check for the system initialization state. Since we will be in this the least amount of time We want to check for it last, so we're not wasting time each loop checking for a state we're hardly going to be in. This institutes a startup delay like you would if you had some sort of power on reset circuit. So it waits 64 clocks, and then it puts the system into a pause mode or a wait mode. And as long as the system isn't stopped, we're going to go ahead and tick the clock half a tick. And we have separate functions for decoding the state based on the input signals, decoding commands sent to it over the serial port, and logging state to the serial port, some helpers for the data bus. And this is a helper function to give us a nice hex display on the serial port with leading zeros. So if I start this up now, oops, let's bring up our COM port here. And we'll compile and run our code on our Arduino over here. So it starts up and says we're in pause mode, and now we can tell it to run. And what we're going to see, we're going to get a debug line for each half clock. So each number here in the data output, you can see how they're all reported twice. That's because we're dumping that debug output every half clock. So this first part here in F8 is the store immediate. So we're storing a 22 to register 1. F8 store immediate, we're storing a 0 to register 1 high. E1, we're setting the X register. And you see here where it says 1802 write, that means we're writing which E input that we're on there. So now if I type in dump, it'll stop it and dump our 64 bytes of memory. And this address right here is the location that gets saved to us. It's saying EF2 is on there, and we can run this again. Demo-itis, it doesn't want to restart. Well, we will cheat and just click play again. And I'm going to change the input jumper over here to number 1. And we'll enter run mode. So we can see what was written was different this time. It's a 4. Now we're looping back around. Writing a 4 out again. Change our jumper position. And we're writing a 1. So what this program is doing is just looking at the state of the EF1 through EF4 inputs and writing them to the memory location, which is hex 22 right here. And we should be able to run this again from this position, but that doesn't seem to want to work anymore. Demo-itis. To test my code before I run it on the actual 1802 with my test rig, I'm using a program called 1802 Simulator, and I'll put the link to this in the description down below. There's also another emulator called Emma02, which is much more full-featured and emulates entire 1802 based systems. This 18.0 simulator is much simpler and much easier to use for what I'm doing. One thing I'll point out, if you click on Option here in ROM map, this sets write protected areas, which would be like ROM. Since I don't want to use that, I'm going to set them all to 0. And you'll see here this will turn from red to white, meaning that we can write on it. And hex location 22 here is where our program will write to. This is the same program we were just running on the test rig. So I'm going to put this in single step mode. Tell it that the EF2 flag is on and step through it. And we can watch the execution trace over here where it does a nice disassembled output to tell you what's going on each line. And you can see up here that it set hex location 22 to a 2. So if we change our input to a 3 and step through it a few more times, you can see it changed to a 3. So this made it really nice because I've been having to hand assemble the code, which I haven't done since the 1980s really. So it's been kind of a flashback from my high school days. Well, I hope you've enjoyed this video. It was certainly a lot of fun and an interesting challenge to get to learn how to test these RCA 1802s using an Arduino. Now, one thing I learned for certain is I really do not like these jumper wires. They're convenient for something like this, but they really don't make a very good connection, and I've had to fiddle with them a lot. So I guess it's kind of a mixed bag there. I'll have some more 1802 videos coming up in the future. I want to experiment with the microprocessor a little more, learn more about it, learn more about the programming, and maybe design some sort of portable computer with it, or like a 1802 based pocket computer like might have existed back in the 1980s. That sort of thing. If you look in the description down below, you'll find several links to some of the things I've mentioned in this video, such as the 1802 mailing list and various sites which have a lot of good 1802 information. And if you have any questions or comments, please leave them in the comments section down below. I would love to hear from you. If you're a subscriber, thanks. I really appreciate it. It helps out a lot. If not, what the heck are you waiting for? If you look down below, you'll see a rectangular subscribe button. So click on that guy and you'll be subscribed. And if you click on that bell-shaped icon, YouTube will be nice enough to let you know just as soon as I post a new video. All of that helps other people find the channel, and it's very encouraging for the content creators to see the number of subscriptions grow. Well, until next time, bye.